Hello viewers, earlier we have discussed in detail about the lanthanides and today we have to discuss about the actinides. In this we have to discuss what is actinide, the general features of actinide, the detailed electronic configuration of actinide, how the electrons are getting accommodated in the f orbital, what are the common properties of the actinide will be discussed, the ionic radii and how the ionic radii is going to decrease which causes the actinide contraction, what are the various oxidation states to be discussed for the actinides and which one is most stable and common, how the actinide ions are developing the color and what sort of complex formation is possible with the actinide elements, that will be discussed, and the similarities and differences with the lanthanide shall also be discussed. The name actinium derived from the Greek word actis, which means beam or ray. The actinium, which is having the atomic number 89 and the succeeding elements up to the lawrencium, the atomic number 103, all these are called the actinides. The first actinide discovered were uranium and thorium. The actinides are mostly man-made element under condition of nuclear reactor except first three elements, namely thorium, protactinium and uranium. Uranium and plutonium are well known actinides due to their application in nuclear reactor and nuclear bomb. Particularly plutonium is used in nuclear bomb. All the actinides are radioactive in nature. None of the actinide have any stable isotope. Actinides occupy the place just below the lanthanides at the bottom of the periodic table. Actinides constitute second inner transition series. The first series is dedicated for the lanthanide, it is the second inner transition series. The element in which additional electron enters in the n-2f orbital are called inner transition element, that is placed in the transition element series of the d block element. Here it is in the f block. Since the extra electron goes to f orbital, which belongs to n-2th main shell in their elementary or ionic state, hence these are called f block elements. In actinides, 5 f subshell being successively filled, the elements in which the extra electron enters 5 f orbital of the n-2th main shell are known as actinides. Actinium, the atomic number 89 and the next 14 metallic chemical element ranging atomic number 90 to 103 which follows it are called actinides and also known as actinones. Since number of electrons in the outermost as well as the penultimate cell remains same, hence all the 15 actinide resemble one another very closely. All these 15 elements of the actinide series have similar physical and chemical characteristic due to this reason. Actinides are also known as second rare earth series placed just below the lanthanide. The lanthanide is known as the first rare earth series. The lanthanide rare earth series placed below the actinides. This is the group of the actinide element starting from thorium up to the lawrencium. It is thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, einsteinium, fermium, mendelevium, nobelium and lawrencium. The uranium used in ceramic glaze, nuclear fuel and nuclear weapon. The plutonium is used as a fuel in nuclear power plant, bomb core and spacecraft propulsion. Americium is used in some home smoke detectors and the californium 252 is used to kill cancer cell. Such type of wide applicability of actinides makes us to learn in detail about the actinides. The curium was named after Marie and Pierre Curie. The berkelium named after Berkeley, California. Californium was named after California. Einsteinium named after Norman Einstein. Similarly, fermium was named after Enrico Fermi. Mendelevium named after Dmitry Mendeleev. Nobelium named after Alfred Nobel. The lawrencium was named after Ernest Orlando Lawrence, who was the inventor of the cyclotron. So, most of the actinide elements were named after their discoverer The existence of transuranium element was suggested by Enrico Fermi based on his experiment back in 1934. At that time, only 4 of the actinides were known. Neptunium was discovered in 1940 by bombarding uranium-238 by neutrons. Then in 1941, plutonium was discovered by bombarding the uranium-238 by deuteron. Americium was discovered in 1944 by bombarding plutonium-239 with neutrons. In 1944 itself, the curium was discovered by bombarding plutonium by alpha particle. Means americium was discovered by neutrons bombarded on plutonium-239, while the bombardment of alpha particle caused formation of curium. Berkelium was discovered in 1949 by bombarding 241 americium by alpha particles, and the alpha particles, when bombarded on curium, it was going to form californium, which was prepared in 1950. The another transuranium element einsteinium was discovered in 1952 as a product of nuclear explosion. Fermium as a product of nuclear explosion again was discovered simultaneously in 1952. Later in 1955, mendelevium was obtained by bombarding einsteinium 253 by alpha particles. The nobelium was obtained by bombarding 243 americium by 15N, the nitrogen, and it may also be prepared with alpha particle interacting with uranium 238. Lawrencium, the last member of the transuranic series, was obtained by bombarding californium 252 by boron 10 or boron 11, and it can also be prepared by bombarding americium 253 with oxygen 18. Let us discuss about the electronic configuration of the actinide series. It is having general configuration 5f 1 to 14, means successive addition of electron in the 5th f, 6d 0 or 1 and 7s. The actinides have similar properties because the 5f electrons, in which alone they differ, are embedded in the interior, while 6d and 7s electrons, which are alike, are exposed more to the surroundings. The actinides have similar properties because of their structure. It is evident from the structure of thorium, protactinium, uranium and americium. These actinide elements, this is the radon, it is accompanied with the 5f0, 6d2, 7s2 type of configuration. The electron is accommodated in the 5th f starting from the protactinium and not from the thorium, and afterwards the successive addition of electron is going to take place, which can be seen that it is having 5f3 configuration for uranium, and later for americium it is having 5f7 configuration. This is the shape of the f orbital, fxyz, fyz square, xz square, fx x square minus 3y square, fyy square minus 3x square and fz x square minus 3y square. So, this is the 3-dimensional structure of the f orbitals. Whether thorium and protactinium and uranium contains any 5f electron or not, the additional electron in thorium, protactinium and uranium enters in the 6d subcell and not in 5th f subcell. The entry in 5f subcell starts only after uranium, not up to the uranium. According to this proposal, the element following uranium in which 5th f subcell is definitely being filled are called uranides or transuranic elements. Uncertainty for 5th f or 6d subcell is due to the fact that both of these subcells are of almost equal energy. Since the energy difference is very less, so it becomes almost difficult to distinguish whether electrons are going to prefer for entry in 5th f or the 6d subcell. Another concept of configuration accepts that 5th f subcell begins with thorium. General electronic configuration of actinide is accompanying with radon, it is 5f 1 to 14, 6d ranging 0 to 1 and 7s 2. In the succeeding 14 elements, electrons are successively added to empty antipenultimate 5th f subcell. According to the modern view, fifth f orbital in actinide starts filling from protactinium, that is having atomic number 91, and not from thorium, which was the previous concept. Tendency to retain 6d electrons exists with lighter members from actinium 89 to neptunium 93. It is due to the very small energies gap between fifth f and 6d orbital in the actinides. Let us discuss about the common properties of actinide. Thorium and uranium are long lived and frequently occur in nature. Neptunium and plutonium have been isolated in traces from uranium mineral. The transuranic elements do not occur in nature and prepared artificially using nuclear reactor. Either it is using alpha or it is using the neutrons. It will be discussed later how the transuranics are getting prepared. All these actinide are metals. All these elements are radioactive and are alpha ray emitter. These actinides are mostly having silvery white color. The hardness of thorium is like soft steel, but some of them are very soft and can be cut with knife, as you might be knowing about the sodium, such type of elements which can be easily cut by knife, they are so soft. But the thorium is having the hardness like soft steel. All the actinides are highly electropositive and reactive in nature. Yes, it is having silvery white color, but it is getting tarnished easily when exposed to air, and it is due to the formation of coating of oxide on it. These elements are very reactive with most of the non-metal, especially when heated. Finely divided thorium burns spontaneously in air. It is similar to that observed with the lanthanides. They resist attack of alkali and also less reactive towards acid. All the actinide except thorium and americium have very high density. The ions of actinide elements are paramagnetic in nature. These actinides form compounds which in aqueous solution give simple trivalent ion which are hydrated as actinium tripositive, uranium tripositive ion, neptunium tripositive, plutonium tripositive and americium tripositive ion. Such type of trivalent ions are being prepared. Let us discuss about the ionic radii of the actinide element. The actinide elements are having the ionic radii which decreases gradually on moving along the ionic actinide series. On going from actinium 3 plus to curium 3 plus, the ionic radius decreases from 1.11 angstrom to 0.98 angstrom, means there is gradual decrease when we move from actinium to curium in +3 oxidation state. The similar steady decrease in the ionic radii of actinides in 4th oxidation state has also been found. This steady decrease in the ionic radii with increase in positive charge of nucleus is called actinide contraction. This actinide contraction is same what was discussed previously in case of the lanthanides, the lanthanide contraction. Here the contraction in ionic radii of actinides in +3 and +4 state of ions may be attributed to the addition of successive electrons in an inner 5th F subcell. Thus, at each step the nuclear charge is going to increase, and further the increased nuclear charge is not compensated due to the poor shielding effect of the 5th F electron. Hence, with increase in atomic number, the inward pull experienced by the 5th F electrons increases, which causes actinide contraction. It is the +4 state of the actinides which goes on decreasing, and similar decrease can be observed for the +3 state of the actinides, and this plot is going to represent the metallic radius in the picometer. Let us discuss the various oxidation states in the actinide. The actinides exhibit oxidation state of +2, +3, +4, +5 and +6. The +2 oxidation state is shown only by the actinium and thorium in compounds like thorium bromide, thorium iodide, thorium oxide and thorium sulphide. All these are having the +2 oxidation state. The +3 state is shown by all actinide elements, and it is again similar to that which behavior was shown by the lanthanide elements. The plus 3 state become more and more stable with increase in atomic number. The plus 4 state is shown by the first 8 elements from actinium to curium. The plus 5 state is shown by 5 elements from thorium 90 to plutonium 94. The plus 6 state is shown only by the 4 elements, the protactinium to plutonium 94. Since in the first half of the actinide series, that is lower actinides, the energy required for conversion of 5th F to 6D is less. Hence, lower actinides shows more higher oxidation states as plus 4, plus 5 and plus 6. Similarly, in higher actinides, the energy required for the conversion of 5th F to 6D is more. Thus, higher actinides shows only lower oxidation state as plus 3. Let us discuss about the plus 3 oxidation state in actinide. A large number of isomorphous salts are given by the elements of actinide series. The trichlorides and trifluoride of actinium, uranium, neptunium, plutonium and americium are isomorphous. On hydrolysis, all the halides give oxyhalides. Actinium, plutonium and heavier elements give oxides of An2O3 types, which are isomorphous with that of the lanthanide Ln2O3 type of oxides. Nitrates, perchlorates, sulfates are soluble, however, the hydroxide, fluoride and carbonates are insoluble in nature. It forms more stable complexes with EDTA. EDTA is highly complexing agent and actinides in the plus 3 oxidation state are capable to form the stable complex. The next is the plus 4 oxidation state in the actinides. It is main oxidation state of thorium and a stable oxidation state continuing up to the americium. Americium plus 4 and curium plus 4 exist only as complex in concentrated fluoride solution of low acidity. The hydrated fluoride and phosphates are insoluble in nature. The thorium oxide, protactinium oxide, uranium oxide, neptunium oxide, americium oxide, curium oxide and berkelium oxide have fluoride type of structure. Tetrachlorides and tetrabromides of thorium, protactinium, uranium and neptunium are only known, while the tetraiodides of thorium, protactinium and uranium have been isolated. Let us discuss the plus 5 oxidation state of the actinide. It is the main oxidation state associated with protactinium and a stable oxidation state continuing up to the americium. Only known pentahalides are those of protactinium in plus 5 oxidation state and uranium in plus 5 oxidation state. The oxychlorides of ANOCl3 type of protactinium, uranium and neptunium are also known. The monovalent dioxocation of type ANO2 plus forms many complexes with anionic and neutral ligands. Let us see the plus 6 oxidation state in actinides. Uranium, neptunium, plutonium and americium shows plus 6 oxidation states in divalent dioxocation of ANO2 2 plus type. Although it is linear in shape, it can form 4, 5 and 6 coordinated complexes with exceptional geometry. The last one is the plus 7 oxidation state in actinide. The plus 7 oxidation state is shown by neptunium and plutonium only. The electrolysis of ozone oxidation gives green solution of neptunium pentoxide with plus 7 oxidation state. It can also be slowly reduced to the plus 6 oxidation state at 25 degree centigrade. Actinide ions are bearing colors. These are having the color which depends on the number of electron in 5th F subcell. The ions with empty 5th F and half filled 5th F subcell are colorless. The ions containing 2 to 6 electrons in the 5th F subcell are colored. The uranium plus 4 is green, uranium plus 3 is red and uranyl ion is yellow in color. So, the species of uranium are bearing the green, red and the yellow color. The color appears due to electronic transition between various energy state within the fifth F subcell, that is known as the FF transition. Let us have a brief account of FF transition. The color appears due to the number of F electrons. The color of ions containing XF electrons is about the same as those which has been seen with 14 minus X F electrons. The absorption band in visible region of electronic spectra arise because of absorption of light in visible range, resulting in transition of electron of ions from lower energy f orbital to higher energy f orbital. Due to this transition of electron, the absorption is going to take place, which causes color in the actinide ions. The color of actinide ions is complementary to the color of light absorbed. Such type of change in arrangement of F electrons, all due to the absorption of light, is known as FF transition. The same phenomena is also applicable for the lanthanides. Let us see the formation of the complexes. The actinides have greater tendency to form complexes as compared to that observed in lanthanide. Most of the actinides halides form complex ion with alkali metal halide, as thorium tetrachloride forms complexes as KTSCl5 and K2TSCl5 with potassium chloride. The thorium tetrachloride and tetrabromide also form complexes with pyridine. It also forms chelates with EDTA. Chelate means it is having ring type structure. The actinides can also form complexes with pi bonding ligands as alkyl phosphine and thioethers. Let us discuss about the similarities with the lanthanide and what are the differences with the lanthanide, because the lanthanide is constituting the first transition series, the first rarer series, and actinide is constituting the second rarer series. So, definitely there is possibility of some similarities and some differences. The lanthanide and actinide involve filling of f orbital and thus are similar in many respects. The most common oxidation state is +3 for both lanthanide and actinide. Both are electropositive in nature and thus both of them are very reactive. The magnetic and spectral properties are exhibited by both lanthanide and actinide. The actinides exhibit actinide contraction same as that observed in the lanthanide, means with increase in the atomic number there is gradual decrease in the size. Absorption spectra of actinide also consist of sharp lines like those observed in the lanthanide. So, these are the similarities which are observed in the actinide as compared to that of the lanthanide. Let us have an account of the differences between the two. The difference arises mainly because of lower binding energy of 5th F electron in actinide than those of 4 F electrons in lanthanide. The 5th F electron provides less effective shielding as compared to 4th F. That is why the difference is available. Besides +3, lanthanide also shows oxidation state of +2 and +4, while actinides show higher oxidation state +4, +5, +6 and +7 as well. The dominant oxidation state in actinide however remain +3 as in lanthanide, but for thorium and protactinium +3 is unimportant and +4 and +5 is going to dominate. The lanthanide ions are colorless while most of the actinide ions are colored. The actinides have a greater tendency towards complex formation as compared to that with the lanthanide. The lanthanide compounds are less basic while actinide compounds have appreciable basicity. The actinides form few important oxocations such as uranyl ion, protonyl ion, like which such oxocations are not known for the lanthanides. Almost all actinides are radioactive while lanthanides except promethium are non-radioactive in nature. Let us summarize the points. Actinides and their position in periodic table was discussed in detail, how it is going to form the second transition series, the inner transition series. Further, the general feature of transuric element, how they were been discovered, and what are the electronic configuration of actinide, how the electrons are getting accommodated in the f orbital was being discussed in detail. The electrons are being accommodated after thorium or after promethium, that was being discussed. The common properties of actinides, either it is its appearance or it is turning tarnish due to the formation of the oxide layer on it. Such type of common properties which are present with the actinide was being discussed. The ionic radii of actinide, same as the lanthanide, was going to decrease. So, discussed the actinide contraction and its reason why the actinide contraction is going to take place. We have seen the various oxidation state of actinide starting from +3, +4, +5, +6 and +7 oxidation state. We have discussed in detail about the FF transition, how the FF transition is responsible for the development of the color in the actinide ions. Further, we have discussed the possibility of formation of the complexes in the actinide. The possibility of complexes with actinide is more stronger as compared to the lanthanide. We have discussed at the end what are the similarities with the lanthanide. The lanthanide are the first transition series and actinide are the second transition series. The similarities we have discussed and also the differences we have discussed in detail. Further, we shall be discussing about the extraction of the actinide elements and production of different elements by the nuclear process.